Hi, this is Miss Gray, and you're in AP Chemistry. You're almost at the end of the year, too. How's that feel? We're in podcast 13.3, and today we're going to look at the relationship between delta G, Gibbs free energy, and equilibrium. Remember, delta G is expressing spontaneity of a reaction. When delta G is positive, then the reaction is not spontaneous. That means it does not favor products, right? And so we can relate this to equilibrium and compare delta G to the equilibrium constant K. So we know that delta G at equilibrium, at standard conditions can be solved for using the enthalpy change at standard conditions and the entropy change at standard conditions. That's what all these little zeros are for, to indicate that we are at standard temperature and pressure, 25 degrees Celsius, pressure of 1 atmosphere, and also at a 1 molar concentration. But let's solve for any quantity here. So delta G that's non-standard will be derived from the standard delta G that's adjusted for whatever conditions we have. In equilibrium, when we had just whatever conditions, we called that Q, where Q is the reaction quotient. Delta G represents the free energy at non-standard conditions, where the circle thing is our delta G at standard conditions. And then the reaction quotient, Q, is what we're using here, so we can put in any old concentration, not just equilibrium concentrations. So this is going to give us some power to deal with non-standard conditions. We define standard conditions to be the set of concentrations or pressures where Q is equal to KEQ. So we're at equilibrium, and delta G is going to be connected to that equilibrium constant. So if you know the value of the Gibbs free energy, then that's going to be a link to finding the equilibrium constant. It's negative RT times the natural log of the KEQ, where this R is the 8.314 joules per kmol, and then T is temperature in kelvins. Remember R, that old gas constant? And then temperature has to be in kelvins. I better write that out. It just looks like ink, huh? And then ln of K is the natural log, not the log log, the natural log of big K, not baby K. Big K EQ. What if we are, though, not at standard conditions? If delta G is negative, then let's write an expression for K. The KEQ is written with products over reactants, right? The concentration of the products over the concentration of the reactants. So if delta G is negative, then that means we have a spontaneous reaction and the products are favored, thus KEQ will be greater than 1 because the products will be greater than the reactants. And so our fraction would be some number bigger than 1. On the other hand, if delta G is equal to 0, then the products and reactants are exactly the same, and our KEQ is equal to is equal to 1, because some number divided by itself is equal to 1. If delta G is positive, then that means KEQ must be less than 1, because reactants are favored. Now let me show you this mathematically too. Okay, so we know that the natural log of 1 is equal to 0, right? So let's come back to our equation. When KEQ is equal to 1, then that means delta G naught equals minus RT times the natural log of 1, and that would make this piece be equal to 0, which multiplies this whole term, RT, and makes that piece equal to 0. Therefore, delta G will be 0 when KEQ is 1. Now let's look at something less than 1, right? If KEQ is some number less than 1, what does that mean mathematically? So the natural log of 0.1, say, there's 1/10, right? That's less than 1. That's a negative value. So come back to our equation. So delta G for a KEQ that's less than 1 means delta G is going to have minus RT times the natural log of 0.1, say. We got a negative value, and a negative times a negative makes a positive. Where delta G is positive, then it's non-spontaneous. We're not favoring products in a non-spontaneous reaction. We're favoring the reactants here. So for a KEQ that's less than 1, delta G is positive or non-spontaneous. All right, last scenario is, suppose that delta G is greater than 1. So I don't need a number that's a whole lot greater than 1 to show you. So let's do 1.5, say. The natural log of 1.5 is a positive number. See that? So if I have a positive term here for my KEQ, this is positive, and then it's minus RT times my positive K, then I'm going to get a delta G that is negative, and that is a spontaneous reaction where products are favored. So that's how this works. We could tell just by looking at the equilibrium expression what might happen with delta G, but now we have some mathematical proof to back it up. Let's look at ways that you know to calculate enthalpy, because I want to show you your flexibility now as a chemist. You see, we've learned 4 different ways to calculate enthalpy changes, delta H. We can use calorimetry because if pressure is constant, then Q is equal to delta H. We also know about Hess's law in the form where we add reactions together, then you can add their heats together. We could also solve for delta H by taking the sum of the products minus the sum of the reactants. And finally, we can use bond energies, where we take the sum of the bonds broken minus the sum of the bonds formed. We practiced that in class just the other day. Calculating Gibbs free energy has a few options for you too. Now you have 3 ways to calculate for delta G. One of the ways is to use the delta H minus T delta S equation. Another way is, sorry, I put them out of order. Another way is to use your equilibrium constant. And then I saved the last one for last, in spite of my crazy animation, because I want to show you how we use the cell potential. So in your electrochemistry unit, I don't know why this is printed all goofy, we're going to use the number of moles of electrons transferred times Faraday's constant times your electrical cell potential to describe the spontaneity of a redox reaction. So that's for electrochem in our next unit. It'll be easy. Wait and see. Let's do a calculation where we can put this into use. So in example 5, we're asked to calculate the enthalpy change, the entropy change, and the standard Gibbs free energy change for this reaction using the appendix in your book. It's Appendix C if you're using the 10th edition of Brown-LeMay. Remember, the thing that we have to be careful of is our units. So let's see, what shall we do? I'm going to make my little chart here and look up all my values. So for delta H, I have negative 296.9 kilojoules per mole. Let's put this in joules right away, shall we? Excuse me. Negative 296.9 times 10 to the third joules per mole. And I have 2 of them, so we'll multiply that by 2. And then for oxygen, since oxygen is an element, delta H is 0 for any element. And for sulfur trioxide, it's negative 395.2. Change kilojoules to joules. Joules per mole. And there's 2 of those, so let's double this value as well. Now let's do the delta H calculation. So the heat of this reaction, standard enthalpy change for this reaction, will be the sum of the products, 2 times negative 395.2 times 10 to the third joules per mole. There's my products, minus the sum of the enthalpy change for my reactants. So I have 2 sulfur dioxides And make sure you've got that in joules, not kilojoules, please. And then we have to add to that the enthalpy change for oxygen, but that should be easy math for you since that enthalpy change is 0. And my result was, let's keep an eye on our sig figs here, joules per mole, negative 196,600 joules per mole. Now let's find the entropy change here for this reaction. Okay, so come back to our chart and we'll find the entropy values in the back of the book. For sulfur dioxide, I have 248.5 joules per kmol. And for oxygen, it's 205 joules per kmol. And sulfur trioxide, what do we have? 256.2 joules per kmol. Now let's apply our stoichiometry. I have 2 sulfur trioxides and 2 sulfur dioxides. So we'll double both of those values, and now we'll do the sum of the products minus the sum of the reactants. So 2 of my sulfur trioxides, that's my products, minus my reactants, so 2 sulfur dioxides, 248.5, plus 1 of my oxygens, just 205 joules per kmol. We'll add those together, and then we'll subtract the products minus the reactants, and I got 189 joules per Kelvin mole. Now we're ready to calculate Gibbs free energy change for this reaction. It's going to be delta H minus temperature times delta S. Temperature must be in kelvins, so let's check this. Yep, temperature's in kelvins. So let's just put our numbers in and work it through on our calculator. Delta H was negative 196,600 joules per mole. And my temperature is 298 kelvins. We'll multiply that times our entropy change, 189 joules per Kelvin moles. So then we get to cancel away the kelvins. We're left with joules per mole minus joules per mole. They're both negative, so the same sign means we need to find the sum. And I get negative 140,278 joules per mole. In kilojoules, that would be negative 140 kilojoules per mole, keeping an eye on our sig figs, of course. And that's how we solve delta G. You've done that before. Now let's use an equilibrium constant to get to a delta G. Oh, no, we're going to go the other way. We're going to use delta G to calculate the equilibrium constant instead. That works. So in this reaction, the synthesis of ammonia, delta G is a negative 33.3 kilojoules per mole. Now look at stoichiometry. It's per mole of nitrogen. All right, so 1 mole of nitrogen is in this balanced equation. That's not going to give us too much heartburn. We are asked to calculate the value of the equilibrium constant. That's the big K, not the little k, KEQ. So we rearranged the equation to solve for K in our previous slide. That's equal to E raised to the negative delta G naught over RT. No problem. Let's just put the values in, but be careful of your units here. Remember, R is in joules per kmol, so we can't have G in kilojoules when R is in joules. So we take E raised to the power of negative delta G. So that's a negative 33.3 times 10 to the third joules per mole. There we go. We've changed joules to kilojoules to joules now because it multiplied by 1,000. And then we divide that by R, the gas constant, 8.14 joules per kmol. And then temperature, T, is going to be 25 degrees Celsius. Do you remember what 25 degrees Celsius is in kelvins? Right, at 273, so we get 298 kelvins. Standard temperature, right? So the value of KEQ, let's put it in our calculator. Okay, so we have E raised to the power of, no, negative, no, not minus, negative, there we go. Raised to the power of negative 33.3, where's my scientific notation? There it is, to the third, divided by 8.314. I hope that's what I wrote on the slide. We'll get there. Times the temperature, 298 kelvins. Yep, there we go. So my K for this problem is 687,336. We don't get to keep all those sig figs, do we? Let's see. Looks like we better keep only 3. So we'll call this 6.87 times 10 to the 5th, and we don't need units because it's a K equilibrium expression, so no units required. If you were dealing with baby K for a rate constant, then you need units, but not for big K. So that's how we change the Gibbs free energy into our equilibrium constant. Pretty simple, right? Let's try another one like this. So in this problem, we're given a set of values where we're not sure if it's equilibrium values or not. So we can't really say if it's G standard. So I'm going to look up G standard in the book. I believe your packet asks you to calculate delta G if delta G standard is equal to, where is it, negative 16.66, because I looked it up for this reaction in my book. Alright, so let's change delta G standard into delta G for any old set of conditions. That means we take delta G naught minus RT times the natural log of Q, where Q is our reaction quotient. We write it just like an equilibrium expression, only now we can put in any old values. So the concentration of ammonia will be raised to the power of 2 divided by the concentration of nitrogen times the concentration of hydrogen raised to the power of 3. So let's put our values in. Delta G naught is negative 16.66. Then we'll subtract the product of the gas constant, 8.314, and that's joules per kmol. Joules. And this one is in kilojoules. So adjust that real quick. There we go. Times the temperature of 389 kelvins times the natural log of our reaction quotient. So let's put those numbers in next. My concentration for ammonia is 2 molar, and that's squared. Then the concentration of nitrogen is 3.01 molar, and the concentration of hydrogen is 1.25 molar. That's raised to the 3rd power. All right, get your calculator ready, and let's crank this through. When I put in all the values, don't forget that we changed kilojoules to joules here. I ended up with Q, by the way, equal to 0.8059, and then we'll take the natural log of that and multiply by all this other stuff. So negative 16.66 times 10 to the 3rd minus the rest. All right, I'm going to just put it in my calculator now. I think I'm ready. So negative 16.66 times 10 to the 3rd minus, we need 8.314 joules per kmol times my temperature, 389 kelvins, times the natural log of Q, which was 0.8059. Alrighty, so I ended up with negative 15962.1, and that is, when we cancel out our K's, joules per mole. Now let's check our sig figs, please. I get to keep, let's see, looks like I get to keep 2 sig figs only. So negative 1.6 times 10 to the 2, 3, 4 joules per mole. Or in kilojoules per mole, it's negative 1.6 times 10 to the first kilojoules per mole, or negative 16 kilojoules per mole. So we didn't have a significant drop in the Gibbs free energy, but we did have a little bit of a drop so that we could adjust and get our whole system back to equilibrium conditions. That's how we use Gibbs free energy and equilibrium together. So now you'll be ready for that. See you guys later.